A bullet train enters a tunnel at 300 kilometers an hour. Seconds later, people hundreds of meters from the other end hear something explode. No crash, no accident, just a wall of air punched out of the mountain like a cannon. This was Japan's problem in the 1990s. They had built the fastest train on Earth, and it was too loud to run. The fix didn't come from a wind tunnel. It came from 3 birds, and each one silenced a different part of the train. Here's the strange thing about going fast. The enemy isn't really speed. It's sound. Push any object through air quickly enough, and it starts to scream. Air piles up, tears into turbulence, and radiates noise in every direction. For a bullet train, that noise isn't just annoying. In Japan, it was illegal. Strict environmental laws capped how loud a train could be in the residential areas it raced past. And the faster engineers pushed the Shinkansen, the harder they slammed into that legal wall of sound. The train that would become the 500 series had 3 specific noise problems. 3 completely different pieces of physics, screaming at 3 different frequencies. And in the early 1990s, one engineer at West Japan Railway solved all 3 by doing something no aerodynamicist is trained to do. He went birdwatching. This is the anatomy of the quietest fast thing ever built. To fix noise, you first have to understand where it's born. At low speed, a train is mostly quiet. The loudest thing is the wheels on the rails. But aerodynamic noise doesn't grow gently as you speed up. It explodes. Sound power from airflow rises with roughly the 6th to 8th power of velocity. Read that again. Double the speed, and the aerodynamic roar can jump not by 2 times, but by well over 100. So when the Shinkansen climbed from 200 kilometers an hour toward 300, noise stopped being the problem. The air itself became the problem. And above roughly 250 kilometers an hour, that airflow noise takes over completely. Now at Japan's geography. Japan is a spine of mountains, so a high-speed line can't wind gently around them. It bores straight through. The Sanyo Shinkansen route is riddled with tunnels, and a tunnel does something brutal to a fast train. In open air, the air a train pushes can spill sideways in every direction. Inside a tunnel, it can't. The train becomes a piston, ramming a column of air down a sealed tube. That compressed air races ahead of the train at the speed of sound, builds against the far exit, and then bursts out the other end as a low-frequency pressure wave. Residents called it the tunnel boom. A single micropressure wave, loud enough to rattle windows hundreds of meters away. That was noise problem number 1, and it was the one that could shut the whole project down. Problem number 2 lived on the roof. To draw power, the train presses a device called a pantograph up against overhead electric wires. Picture a rigid arm, held high into a 300-kilometer-an-hour hurricane. As air rips past that arm, it peels off the back edge in a chaotic street of swirling vortices. And every one of those vortices is a little pressure pulse, a little pop of sound. Thousands per second. Together they blend into a piercing aerodynamic whine. Worse, that pantograph sticks up above the smooth roofline, right out in the open, with nothing to shield it. On a high-speed train, the pantograph is often the single loudest aerodynamic source on the whole vehicle. That was noise problem number 2. And problem number 3 was hiding in plain sight, right underneath problem 2. The support. The pantograph doesn't float. It's held up by a shaft, a supporting column bolted to the roof. And any blunt shape held in fast airflow does the same ugly thing. The air flows smoothly around the front, then separates. It detaches from the surface and collapses into a turbulent, roaring wake behind. Engineers call it flow separation, and it does 2 things at once. It drags the train back, wasting energy, and it generates broadband noise. 3 problems. A pressure cannon at the tunnel mouth. A screaming arm on the roof. A roaring column beneath it. 3 different frequencies, 3 different mechanisms, and the noise laws demanded that all 3 be beaten at once. So how do you kill 3 kinds of noise in 3 different places without slowing the train down? This is where the story turns strange. The man handed the job was Eiji Nakatsu, a general manager of engineering at West Japan Railway. But Nakatsu had a second life. He was a devoted member of the Wild Bird Society of Japan, a serious, lifelong bird watcher. And that hobby had trained his eye to notice something engineers routinely miss: that nature has been solving high-speed fluid problems for 60 million years. Birds move through air and water fast, silently, and efficiently, because the ones that didn't died. Nakatsu began asking a heretical question for an engineer. Not what machine solves this, but what animal already has. 3 problems. He would find 3 answers, each with feathers. Start with the loudest one. The tunnel boom came down to one thing: the shape of the train's face. The old bullet nose was rounded, almost like an airplane's, great for slicing through open sky, terrible for entering a tunnel. When that bluntish front hit the sealed tube, it slammed the air like a fist, creating a steep, sudden pressure spike. And a steep spike is exactly what becomes a loud boom at the far end. The physics said the answer was a longer, sharper, more gradual nose. One that would ease into the air column instead of punching it. But sharper alone wasn't enough. Nakatsu needed the exact profile. The specific curve that moves between 2 fluids of wildly different density with the least possible shock. And one afternoon, watching birds, he realized he'd already seen it. A kingfisher diving. Think about what a kingfisher actually does. It sits above a river, spots a fish, and drops, plunging from thin air into dense water in a fraction of a second. That transition should be violent. Water is roughly 800 times denser than air. Hitting it at speed should mean a huge splash, a shockwave, a spray that warns every fish for meters around. But the kingfisher barely disturbs the surface. Its strike is almost silent. The secret is the beak, long, and tapered in a very particular way, not a simple cone, but a shape whose cross-section grows smoothly from a fine point back toward the head. That geometry lets the water slip outward gradually, instead of all at once. No shock, no wall of spray. To Nakatsu, the parallel was exact. The kingfisher moving from air to water was his train moving from open sky into the trapped air of a tunnel. Same problem. The bird had a 60 million year head start on the solution. But this is where the story becomes real engineering, not just a nice metaphor. You can't bolt a beak onto a train. The team had to prove the shape was optimal and turn a bird's bill into buildable steel. So they tested. They fired model bullets of different nose profiles through a pipe and measured the pressure waves each one produced. They ran the numbers on how sharply pressure rose for each shape. And the data converged on something remarkable. The profile that generated the smallest pressure wave, the quietest possible entry into that tube of air, was almost identical to the cross-sectional shape of a kingfisher's beak. Nature's answer and the math's answer were the same answer. The result was the face of the 500 series, a nose stretched out to roughly 15 meters, longer than some train cars, tapering with that unmistakable kingfisher profile. It looked less like a train and more like a bird aimed down the track. And it worked. The redesigned nose flattened the pressure spike at the tunnel entrance, which meant a far gentler wave arriving at the exit, taming the boom that had threatened to make the whole train illegal. But the kingfisher nose paid a second dividend nobody bought it for. That same long, smooth taper-cut aerodynamic drag across the entire front of the train. Less drag means less energy to hold speed. And part of why the 500 series ran faster and leaner than its predecessors traces straight back to that beak. One bird, one shape, 2 winds, a quieter tunnel, and a more efficient train. But the face was only the loudest problem. Up on the roof, that pantograph was still screaming into the wind, and the bird that would silence it hunts in total darkness. To understand the fix for the pantograph, You have to understand a different kind of miracle, the silent flight of the owl. Most birds make noise when they fly. You can hear the whoosh of wing beats. Owls don't. A barn owl can sweep down onto a mouse in near total acoustic silence. And that silence is the whole point. It hunts by sound, so it cannot afford to make any. If the mouse hears the owl coming, the owl goes hungry. 60 million years of that pressure produced one of the most sophisticated noise suppression systems in nature. And when Nakatsu looked closely at how an owl kills the sound of its own flight, he found the answer to a problem screaming on the roof of his train. It came down to the leading edge of the wing. Look at the front edge of an owl's primary feathers under magnification, and you don't see a smooth line. You see a comb, a row of tiny, stiff, evenly spaced serrations. Biologists call them fimbriae, jutting out into the oncoming air. On any other bird, the air rolling over the wing separates into a few large, turbulent vortices, the swirls that make the whoosh. The owl's comb does something clever. It shreds that airflow into many tiny vortices instead of a few big ones. And here's the key. Small vortices carry far less acoustic energy, and they scatter across a frequency range that the owl's prey and our ears struggle to hear. The owl doesn't eliminate turbulence. It breaks it into pieces too small and too quiet to matter. Nakatsu had his second answer. But before we bolt a comb onto a bullet train, the third bird is still waiting, and it solves a problem the other two created. So the engineers did something that sounds absurd until you see the data. They cut serrations, a row of comb-like teeth, into the pantograph. Specifically, onto the surfaces meeting the airflow head-on, they added arrays of small vortex-generating fins, mimicking the owl's fimbriae. And it behaved exactly like the wing. The rushing air, instead of peeling off the pantograph in big, loud vortices, was chopped into a fine spray of tiny ones. The piercing whine dropped. In the language the team used, they had built a vortex generator, a phrase borrowed straight from the biology. It's the same principle you'll now find echoed on wind turbine blades and aircraft wings. Deliberately trip the airflow into small-scale turbulence to control the big-scale kind. But an owl's feather is soft, curved, alive. A pantograph is rigid metal in a gale. Translating one into the other took years of wind tunnel work. Proof that biomimicry is never a copy-paste. It's a translation. Which brings us to the third bird, and the problem the owl couldn't touch. Silencing the pantograph's arm was only half the roof. The support holding it up, that blunt shaft, was still dragging and roaring with flow separation. What the team needed was a shape that could hold airflow attached to its surface for as long as possible, delaying the messy separation into a turbulent wake. Nakatsu found it waddling on the ice. The Adelie penguin looks almost comic on land, but its body is a masterpiece of fluid dynamics. A smooth, spindle-shaped form evolved to slip through water with minimal resistance. That same profile, applied to the pantograph's supporting shaft, kept the airflow hugging the surface far longer, delaying separation, cutting both the drag and the noise it produced. Three birds now. A kingfisher for the face, an owl for the arm, a penguin for the column, each solving one specific, measurable problem. So what did three birds actually buy? When the 500 series entered service in 1997, it was the first Shinkansen to run at 300 kilometers an hour in regular service, and it did it while ducking under Japan's brutal noise limits. Reports credit the redesign with cutting air resistance by around 30% and trimming energy use significantly compared to the trains before it. The tunnel boom was tamed. The pantograph's whine was pulled down. Passengers got a smoother, faster, quieter ride, and the people living beside the tracks got their peace back. It's one of the most celebrated examples of biomimicry ever built. The poster child, wheeled out in every design textbook and TED Talk. Which is exactly the moment we should slow down. Because the neat version of this story, engineer sees bird, copies bird, train goes quiet, is a little too neat. And the honest version is more interesting. Here's the pushback, and it's fair. First, The kingfisher nose wasn't a one-afternoon eureka. It was years of testing, hundreds of simulations, and heavy mathematical optimization. The bird gave a starting point, not a finished blueprint. Skeptics argue the team might well have arrived at a similar long, tapered nose through pure aerodynamic math alone, bird or no bird. Second, some engineers point out that later Shinkansen models moved away from the exact 500 series shapes. The pantographs and noses kept evolving, which suggests the bird solutions were a step, not a final truth. And third, the deepest critique. Biomimicry can become storytelling. It's tempting to slap a bird on the front of an engineering decision because it makes a better story than "we ran 10,000 simulations." So is the bird tail just a myth with good PR? Not quite. And here's the case for the other side. Nakatsu himself was careful about this. In his own account, the birds weren't magic answers. They were inspiration that pointed the engineering in the right direction, and then had to be validated with rigorous testing. That's not a weakness of the story. That's exactly how good biomimicry works. Nature doesn't hand you a finished part. It hands you a principle that already survived 60 million years of brutal testing, and says, start here. The kingfisher didn't design the train. It saved the engineers from searching a near-infinite space of possible shapes blind. And the deepest point stands regardless of how much math came after. The winning ideas, gradual pressure transition, microvortex noise shredding, delayed flow separation, all existed in living animals first. Evolution is the oldest R&D lab on the planet. The engineers just knew how to read its results. Step back and look at what really happened here. 3 separate problems in physics, a pressure shock, a vortex whine, a separation roar, were each matched to an animal that had already solved that exact piece of physics for its own survival long before humans existed. The kingfisher never knew it was solving a compression wave problem. The owl wasn't thinking about acoustic energy spectra. The penguin wasn't calculating boundary layer separation. They were just alive, shaped by relentless pressure into forms that happened to be optimal. And that's the quiet lesson underneath the quiet train. The natural world is a library of solutions to problems we're only now learning to ask. Most of that library has never been read. The 500 series is what happens when one engineer, trained to see, finally opens a single page. The 500 series eventually retired from its top-tier routes, replaced by newer trains with their own refinements, some borrowing these ideas, some moving past them. But its face is still iconic, still parked in museums, still instantly recognizable as the moment engineering stopped fighting nature and started listening to it. And the deeper approach didn't retire at all. Today, biomimicry shapes everything from wind turbines to swimsuits to the fans in your computer. The birds were just the beginning. So here's the question I want to leave you with. If the fastest, quietest train of its era was hiding in a kingfisher's beak all along, what other solutions are out there right now, flying and swimming past us, while we hammer away at problems in wind tunnels? What are we still not seeing? Tell me in the comments. If this changed how you look at the natural world or the machines around you, that's exactly what this channel is for. One deep dive every single week into the hidden engineering of the future. Subscribe so the next one finds you. And trust me, you'll want the next one, because we're staying with speed, but this time, we're leaving the ground. Next up, the sound barrier. Not a tunnel boom, but a real one, and the decades-long fight to build a supersonic jet quiet enough to fly straight over your house without shattering a single window. The birds silence the train. The question is whether physics will ever let us silence the open sky. That's the next video. Catch the pulse and lead the future. I'll see you there.